Mấy cái khác.
Distinguished members of the committee, dear colleagues,
ladies and gentlemen. My name is Xin Kai, and I'm a professor at the Department of Informatics, University of Oslo. As the appointed moderator, or Custos, it is a pleasure to welcome you all to this dissertation on the dissertation submitted for the degree of PhD at the Faculty of Mathematics and Natural Sciences at the University of Oslo. The faculty's PhD program council granted Anastasiia Grishina application for admission to the PhD program on the 5th of July, 2021. On the 22nd June, 2024, Anastasiia Grishina submitted her dissertation entitled Software Engineering and its Application with Large Language Models. The supervisors for this work were Professor Leon Moon, Similar Research Laboratory, Norway, Professor Magne Jørgensen, Similar Research Laboratory, Norway. On the recommendation of the Department of Informatics, the faculty appointed the following adjudicating committee. Professor Martin Montperes, KTH, Royal Institute of Technology, Sweden. Assistant Professor Jie Zhang, King's College, London, UK. Professor Paul Halvorsen, Department of Informatics, University of Norway, and Similar Research Laboratory, Norway. The adjudicating committee reported on the 13th of August, 2024, that it had found the dissertation worthy of being defended for the degree of Philosophia Doctor. The candidate presented the required trial lecture on a prescribed subject entitled Machine Learning for Code Generation. The adjudication committee has found the trial lecture satisfactory. During the disputation, the first opponent, Professor Martin Montperes, and the second opponent, Assistant Professor Jie Zhang, will act as opponents. First, the candidate will give us a brief survey of the purpose of the work and the results of the investigations. Then, Professor Martin Montperes will put the work into an international context and present his opinion of the dissertation. Afterwards, Assistant Professor Jie Zhang will continue the opposition. The candidate will be allowed to answer the comments or questions from the opponents. Finally, it will be possible to speak ex auditorio. I now call on Anastasiia Grishina to present her scientific work.
Thank you. I'm just checking the microphone. Yes. And setting up the timer. Hello, and welcome to this presentation on my PhD thesis on software engineering and its automation with large language models. And we'll start with the scope of my thesis. I worked with software development, which has many steps, but there is one step that is code maintenance, where we aim to find errors and correct them, and in our case, automatically. There's a lot of potential to automating this specific step of work, because up to 50% of developers' time is dedicated to debugging, while it can be dedicated to useful, creative feature engineering or software development for new products. So that's why automated program repair as a field has several approaches in it, and I will be focusing on the learning-based, where we have code bases from which we can learn bugs and their fixes from software developers. Now, how do we approach it? A recent hypothesis on naturalness of code states that statistical properties are shared for, or are similar for code and for natural languages. That's what allows us to use language modeling methods, and specifically large language models that have been popular so recently, to automation of program repair. So my thesis will focus on this part of learning-based automated program repair, and I will introduce this term bug lifecycle. That is something just for you to go through maybe this paper-based thesis more easily. First, we need to detect bugs, whether they are there or not in code. We need to localize them, which files or code lines the bug refers to. Then we need to repair and test whether our code or our repair has broken something else in code. And if it doesn't, we need to integrate updates. As I said, it's a paper-based thesis, works on bug detection and repair, and it consists of 4 papers, 1 on bug detection, 2 on bug repair, and one of the paper is an extension of another one. So here you will see like 5 in total papers, and another one I will introduce from a larger scope on language models for software engineering. But I will start with the one that works, the work on bug detection. And it's titled Early Bird and published in FSC, Foundations of Software Engineering Conference. It deals with smaller models and uses early layers of language models to represent code and further classify code into buggy or not buggy. So we have an input source code sequence. It can be in Python, Java, it can be a full function or maybe several lines, but we need to first make it understandable for language model or for a transformer part of encoder that we are going to use. So we first tokenize it, and we append and prepend some special tokens. So for example, first token is called CLS. It's also start of sequence token that we just call CLS. Then token 1 to token n, they correspond to code tokens, so like subwords that we can detect in code, and we also append the end of sequence and padding tokens. Now, all of these tokens, they are passed to the neural network with several layers, and before classifying the code into buggy or not, we need a full representation of coding sequence. And we take it usually from the last layer and the first CLS token from this last layer. Then we pass it through a classification head and classify into buggy or clean code. However, there's information in these first layers that can be also used to get a richer representation of code and hopefully classify better into buggy or clean code. So that's exactly what this work does. So instead of using first token of the last layer, we can somehow combine information from all of the layers and create hopefully a richer representation that will help us classify code. So that's where we need to apply our combinations of early layers, and that's exactly what we did in this work. We applied 2 sets of combinations. One set does not change the model size significantly, and another is pruning that decreases the model size. Now, how did we evaluate this? We used CodeBird as our language model. It is an encoder model with 12 layers. We fine-tuned the model with those combinations and evaluated it on 4 datasets. So we have 2 bug detection datasets, 1 classification dataset where we classify into 3 classes and 1 into 20 classes. We ran the experiments, fine-tuning and evaluation experiments 10 times so that we can see how repeatable they are. With the combinations of the same model size, we can see that some of them perform better, but some of them perform on par or maybe even worse because we have maybe too much information for too small and simple of a task. But what is more interesting is performance of smaller models. So pruning is about reducing the number of layers that we have in the model. We had 12 layers, and when we can, in our case, we just cut off later layers and use only the first ones. So let's say 3 or 4 or 5 first ones. With pruning, we could see that simpler tasks can be approached with smaller model without loss of performance and even with some gains. Here I show results of CodeBird on 2 bug detection datasets. Baseline is CodeBird when we use first token of the last layer and the full model. And then we use also full-size model, but an intermediate layer, as well as smaller model, but first token from the last layer. So smaller models have higher accuracy, and they use less layers, so less energy for training, less resources as well. That was somewhat an unexpected result, but it's great to also see whether it generalizes to more classes in the classification dataset. And we could see that there is a trade-off between performance and resource usage when we reduce the number of layers in 3 and 20 class classification datasets. So we could see that when we remove 1 last layer or 2 or several, we don't see the dramatic drop of performance in terms of accuracy, but here datasets are also unbalanced, so F1 graphs would look very similar. In any case, we could see the trade-off between performance and speed up. So maybe reducing the model size to several layers, but not like 3 or 2, would be good in production environments where we need to take care of resource usage. These were results on bug detection. Next papers would be focusing on bug repair. One of them is fully autonomous programming with large language models, published at Gecko, and also is now under revision process for an invited journal extension to Tello. The motivation here is that software engineers, we iteratively write, update, and fix code. We don't just write it and let it live just its own life without updating it at all, because it may be incorrect, so it can be improved. However, from the large language models perspective, the common practice is to generate code just once and evaluate the results. As a result, we have small imperfections, or maybe even big imperfections, depending on the quality of the model. So we have imperfections, or what is called a near-miss syndrome, where code looks similar to correct code, but has some small errors sometimes, or even big ones. There's one approach to already improve it and debug code that is already generated. However, there's genetic programming and evolutionary algorithms where the common practice is to evolve programs generation by generation, keeping the best programs in each generation and then updating the programs further so that they pass more tests or have less bugs. And that's where our approach also sits. So in between the two worlds, where we use the best of the genetic programming, but also language models for generating new generations of programs. So CIDR is the name of the method. It works by iteratively generating code, explaining errors in it, and correcting them until all tests pass. CIDR stands for synthesize, execute, instruct, debug, and rank. And I will walk you through how it works. We first get a task description from, we used two program synthesis benchmarks. One is program synthesis benchmark from genetic programming and one from language models. We also use several tests just to show what type of tests this program, final program will be exposed to. And we provide those to the template. Now, we have the synthesize block that, with a language model, synthesizes the first program. We use several language models in the first initial experiment codex, and then 2 more models, newer ones. Now, we test this program. We git committed because we just have one program here, and in the test part, we actually use this. It's a part of rank block, or execute block, sorry. Then we commit it because we just have one program for now, and we describe bugs if this program doesn't pass all the tests. We use an analogy of rubber duck debugging that is somewhat humorously used in software engineering, where a person would explain to, let's say, another person or a toy next to the computer what goes on in the code, and by talking around about the program, would maybe find bugs or logical errors. And this description of bugs is also generated by another language model. So we have 2 language models talking to each other. One generates code and generates updates to code, and another explains what the code does and what can be a bug, leading to the failing test. This is powered by a language model and also more of the code-to-text or just text generation models. Now we have one program, and we need to generate several programs from it. So we are going to build a tree of programs, as it is frequently done in genetic programming approaches. So now we need to use this first model that was generating programs and debugging them. So we will debug with the language model, the same models that were used for first initial generation. And the debug block consists of the following steps. For each program in a generation, we need to generate, let's say, several new programs, in this case 3, program 2, 3, and 4. We test them all, so we apply again the execute block. We rank them and only keep the top M programs, in this case 2, just for this experiment, and rank is powered by 2 methods. So we commit the best program that we have found so far, and we explain bugs if those programs still don't pass all the tests. Now we just repeat this whole process. From one of the programs in the generation, we generate 3 more, test them all, keep only the 2 ones that we also commit, as well as they improve, and also find out that actually program 7 is the one that passes all the tests. So we can also test it on the held out test set. Now that's how CIDR works, but how does it perform? With Codex, GPT-3 model trained on code, it outperformed the genetic programming method, PushGP, solving 19 out of 25 Python problems in PSB2, so in a competitive programming benchmark that is harder than human eval that is usually applied for language model evaluation. Here, triarity means that how wide of a tree we are building. If we build a tree with triarity 1, we just only keep one program, and we update it step by step without regenerating anything in parallel. If we have an infinite triarity, it means that we do not keep updating any of the programs, we just discard all the programs that do not pass all the tests and regenerate a new one. So what we found out is that something in the middle, a moderate triarity or moderate width of the tree works best. In the sense that it helps find more solutions than in other benchmarks. And in C++, we were performing on par with PushGP. Now, we work with language models, so we provide several prompts to language models. It's nice to know how different prompts perform. We found out that CIDR is robust to variations in prompts. We used static and modal-based summaries of the bugs. So we used 6 static and 4 model-based ones. We generated only 5 programs in the tree here. Before, we generated 1,000, so the results were better overall. But here, we don't see that any prompt is like leading. However, for C++, there was slightly better performance with prompts that show high confidence, such as obviously the error is, and the language model would then summarize what the error is, and this summary would be useful for the next model to actually generate a debugging update. We also performed a generalizability experiment with 2 other models and a human eval dataset that is more applicable in language models evaluation. We do not see the same trend about the moderate triarity anymore. However, with GPT 3.5, we could still see that CIDR, by iteratively updating the program that does not pass all the tests, it increases or improves the performance over just discarding and regenerating more programs. So these iterations that we have proposed in our CIDR method, they actually improve the performance over just using the model. So this last part where we have infinite triarity, it's also just like using the model without any iterations. So as if we were just evaluating the model without CIDR. That covers CIDR method for program repair. And there was another proposal for program repair that we have, or I have in the thesis. And it's round-trip translation. It's now under review in the DOSM journal. And the prehistory about this, or motivation behind it, is that I moved to Norway to work on my PhD, and I started learning Norwegian. I also used an online translation tool that would helpfully mistake my errors for typos and correct them when I would translate from Norwegian to English. So when I would translate back from English to Norwegian, it would correct my errors automatically. I thought maybe it's a good approach to also apply to code. So if we get buggy code and we pass it through a language model that would translate, let's say this code is in Java. So it would translate from Java to, let's say, Python, C#, or maybe even natural language explanation of what the code does. Then we can translate it back to Java and see whether the code is fixed now. That's what we were trying to check, and we could get already some small proofs of concept where we would repair buggy code in Java through translation to Python or natural language. But how does it work on scale? To check that, we have set up 2 sets of experiments. One with translation through a programming language, for example, C#, C++, or Python, so from Java and then back to Java. And then another set of experiments through a natural language explanation of what models would think the code does. So we could see on 4 benchmarks, including the Facts4J, QuicksBugs, and human eval, but Java, we could see that round-trip translation through natural language, where we have a summary of what the code does, they perform better than this round-trip translation through a programming language. Also, we have found out that our method does not outperform other methods that are specifically fine-tuned, so language models that are specifically fine-tuned for repair, because we used either general-purpose language models or those that are fine-tuned for translation. However, we found out that we could solve problems that are not solved by those benchmarks. So we don't solve more, but we solve some unique ones. Here you can see Venn diagrams where we show what or how many problems were solved by language models with fill-in-the-middle objective training for repair, and then also our models without any further fine-tuning on our methods. So yeah, we do not maybe solve more, but we solve unique ones. Now, that has been that has been a summary of 3 papers, 3/4 papers. It depends on how you count the extension. And now, before introducing the last paper, I would like to maybe step a little bit back and look at, okay, we are using language models for software engineering, and we have worked on bug detection and repair. So we were somewhere here in learning-based methods that are powered by language models, and they are for automated program repair. But if, as I said, we have a step back and focus on the whole software engineering and all language models that are used for software engineering and trained for it, we could see that they require a lot of energy, but it's nice to evaluate how sustainable they are in the sense, do they share code, do they share models, or how maybe open and reproducible they are? Do they share models, code, and how much energy or carbon emissions would the training be associated with? And that's what the 4th paper is about. It's a literature study, and it's published in SM. And there the motivation, as I briefly mentioned, that language models use a lot of resources for training and development. And in terms of carbon emissions, training the models, language model is 5 times more expensive than an average car of a lifetime, and it's a very large number. And those numbers are taken from the paper cited here. So we decided to have a look at how many publications share models in addition to code. We had some inclusion-exclusion criteria that led to about 300 publications in the first stage over the time between 2012 and 2022. Now, about 40% of them do not share artifacts at all, code, data, or models. 33% of them do share code and data, but don't share models. And then 27 do share the models that other researchers can reuse just out of the box and then not spend that much energy and time retraining them. And now we were also interested in how much carbon emissions would be, how many carbon emissions would be associated with training those models that are shared, but also share enough information for calculating these carbon emissions. So they should share what type of GPUs they used, what type of CPUs, and for how long as well. And it also depends on how many models they shared. It was only 10% for which these carbon emissions were, available for evaluation. So the outcome or the lessons learned is that it's important to share the models, not only the code, and avoid expensive retraining. So in addition, maybe we avoid expensive retraining, but we still need to use those models, so it's important to share what type of GPUs or other compute is needed to actually run those models, and what model is best for what task. So during the trial lecture, I was asked what is the best model for code generation, and maybe that's because it's not so explicitly shared in all of the papers, because they just test on one or another benchmark. We don't have like this overview right now that would say this one model is ultimately the best for everything. So it's nice to share those details as researchers and maybe claim, but also when we can claim that they are the best for this or another task. These were my four papers that also make the basis of this thesis. But what would I say this thesis brings to the research landscape, sort of? So I have looked into program repair and its automation and automation of bug detection as well with some innovative uses of LLMs. And I have not always fine-tuned the models, but I would use them in different ways. So in paper one, we reduced the model size, and we were quite surprised that with smaller models, with really simpler models to also train, we could see improvement on bug detection, on the bug detection dataset. CIDR, the second paper, it iterates how we use language models. It doesn't use them just once, and if we evaluate results, we iterate over the process of debugging and updating code, just as software engineers would normally do. Then in our third paper, we would use language models that are trained for a completely different tasks. They are fine-tuned for translation or for general purpose tasks, and not for repair, but we would create such a pipeline that would enable them to repair maybe not more bugs, but some unique ones. And those, CIDR and RTT, those can be tools in multi-agent frameworks where they would maybe contribute to repairing errors, and maybe the RTT part would contribute to some tricky errors that are best to just, okay, let's just forget about the code that we have, let's explain what it does in English and then regenerate it back. So if those usages are important, then yeah, maybe the RTT is a good addition to those multi-agent frameworks. And then it's always nice to step a little bit back and reflect on the energy usage and ensure usability of the models, because now language models are large, they have billions of parameters and are trained for days and weeks, etc. So it's nice to have open and reproducible research. That concludes my presentation. Thank you.
Anastasiia Grishina for her contribution. And now I call Professor Martin to put the work into an international context to give his evaluation of the dissertation and start the ordinary opposition.
Very good. Thank you, Anastasiia, for this. Check. Thanks for the presentation. It gives indeed an overview of the 4 different parts of your PhD, which are different in nature to a large extent. To put things in context, you started in 21, where it was the very beginning of GitHub Copilot, and so GitHub here made a splash on language models for coding. So the research area was already quite active, but still it boosted the research area significantly. And then later on in December 22, we had ChatGPT coming in and bringing a lot of energy and a lot of money in the field, and lots of competition as well. So first thing to understand your work is that you were evolving in an extremely active storm, with lots of competition, lots of data, lots of models, and you had to navigate in that difficult conditions. And I think you did it well. So trying to identify unique angles on the field, and that's good. In particular, I would put CIDR as emphasis, because this notion of iterative prompting. And today we'll have questions about this, is agentic aspects of LLMs is important. And when you did it, it was one of the first to do it. So you had some real novelty here. So the work is significant for the community, significant for industry, and happening in a very active, hot area. And so you were able to make contributions and to publish papers in that context. So that's good. So that's for the overall context of your work. So I have quite a few questions. I will ask a few, then pass the mic to G, just to have a good balance.
Yep.
And I will first focus on paper 2 and 3, because this is my core turf. So and then we'll see. So for paper 2, so actually for paper 1, 2, and 3, the major question is how you define a bug. So what's a bug? How do you define it abstractly and concretely?
Yes. So we define bugs as errors in code of any nature, logic, or it can also be vulnerabilities, because we worked in paper 1 for on defect detection. So we do not specify, narrow down to any specific type of bug, but we worked mainly on function level or line level, like one-line level bugs, and they would be of various nature. And we've also worked on syntactic bugs, or errors in syntaxes, errors in logics, and in semantics, and the vulnerabilities.
Okay, thanks for the answer. Then we can continue in this direction. So there are different kinds of bugs in this world. So for instance, a syntax error, like a missing semicolon, is very different from a logical error. And there are bugs which can be defined according to some kind of specification, so according to an expected behavior. Mm-hmm. And bugs that can be defined because there are more anomalies in the code. So they don't violate any given expected behavior, but they are anomalies. So for instance, a missing semicolon is such an anomaly. But if I have a method which is called subtract and it returns a plus b, it's not a bug per se. It's a bug according to the specification, according to expected behavior. So where does your work fit in that space with bugs as anomalies versus bugs as violations of expected behavior?
Yes, I'm taking time to think, and I would pose it more into violations of specifications. We worked more with those methods that work from instruction, like what the code should do, to generating code. So we had the specification already at our hand. While anomaly related bugs, they can be So in Cider, for example, there would be bugs of that lead to not passing some tests according to specifications, but it would also be just some random next token predictions. So that can be an anomaly, that just token that does not fit here at all. But then it would be more on the language modeling. So I'm also thinking a little bit out loud when I'm responding. I would say that in the majority of our work, we would lean on the specification of violation. But we do not distinguish it as that in our papers.
Okay, so let's take paper 1, for instance.
Yes.
So what is the specification part of the input of the network? The expected behavior.
There we do not have specifications. We have code that either is buggy or not. So because we have the data set that is in the form of a lot of code samples. And in each code sample, we already by dataset construction, we have a bug or not. But for that one, we don't have specification. We just assume that those codes were for some form of specification already.
So here, if I understand correctly, I believe that paper 1 is fully anomaly detection.
It's detection of bugs.
It's really anomaly detection because you don't compare against any expected behavior.
Compare, no.
So it's pure anomaly detection in the code. Do you agree, disagree?
Anomaly detection in code. It's detection of bugs in code. It's detection, we don't have specifications. That's correct. We do not pass specifications together with code or don't have doc strings. So for paper 1, I tend to agree, but for for Cider, for example, we did have specification. But paper 1.
Yeah, so Cider, I agree. Do you run the test for every single generation?
Yes.
So then indeed it's part of the. So this is the expected behavior. For paper 3, round-trip translation is. So the benchmarks you use are based on expected behavior, but since you don't give the failing test as part of the input, as far as I understand.
Exactly.
So it's more anomaly detection.
It's anomaly detection, but sometimes when I'm sorry that I'm interrupting you, is that okay?
It's perfectly okay.
Okay. So once we translate, let's say, from programming language to natural language, then we tend to have the specification, and then when we translate back, then we translate from specification to the fully working code that we can test. However, in the beginning, in the beginning we have the buggy code, and it may not contain docstring, but these docstrings are there. It's like Quix bugs, for example. These are, sometimes by function name, like GCD or something, we can already deduct what the program should do. So specification, as in a separate specification that cannot be guessed from the function name. We don't have it in the very beginning in RTT, but we have it in the middle, in the intermediate representation. So there I would say, yes, we may solve anomaly type of bugs, but through getting a specification when we would get to a natural languages intermediate,
Yeah, which I agree. Lingering question is, in the RTT, do you remove the Java doc as part of the input before going to the other representation?
What we keep is the function name of arguments, and then we tried to generate some doc strings in addition to, but mainly we keep this function signature.
Okay. One more question on RTT, and then good. So for RTT, what I like very much is so how I read your experiment is not more as a parameter experiment, but as more like, again, as a specification exercise. Am I able to generate the specification, the natural language specification from code, and to go back to implementation from that specification? So that's round trip, reverse to implementation. And to that extent, whether but you start from the buggy code. So do you have the number of cases or the proportion of cases for which you can come back to an equivalent solution per the test cases of the initial buggy code? Like you don't fix the bug, but you still pass all the existing test cases.
I may check the numbers, but for translation through a programming language, for example, through C#, because it was so rather close in comparison to Python versus Java, we would arrive at the buggy code again. So the translation was the translation models were so good that they would replicate the same bugs, but I may not have numbers here. The numbers, I have numbers of like solved bugs, and they with PL-BART are like less than 10 in benchmarks. It means that the bug was preserved because the programming language, as intermediate translation, was too close to the initial, so the anomalies were kind of saved, even though we tried to rely on the regression toward the mean. That would be removing bugs from our code because it's more natural to have not buggy code, as shown in some papers.
Okay. So I continue with precise questions on paper 2 and paper 3, then I give the mic to G, and then we'll come back perhaps afterwards. So paper 2. So just about the title of your paper first, so fully autonomous programming, this is very ambitious.
It's very ambitious.
So can you elaborate a bit on the vision here? So what the input of this fully autonomous programming loop?
Yes, exactly. Yeah. So we have a task description as would be in like natural. It's in natural language, and we would maybe also involve a little bit of programming by examples. But why fully autonomous programming? That's also how we. How we keep all the programs available or we keep them all available, all the generations available in this GitHub repository, how we evolve programs. So we automate software developer sort of approach where software developers would start with, okay, I understand this problem now. On this small set of examples, it would work like this. Then there is this first iteration, and we would maybe commit it to GitHub or to some Git checked repository, and we would update our code from there. So it was more hinting on how the what processes we would automate. So because we automated this commit to a separate repository where we would have all the evolution of solutions. And that's what was the main reason behind saying it's fully autonomous. So from natural language to the program that passes all the tests with commits in the middle.
Okay, so the first input is a natural language description of the task, is what you're saying. And the test cases, are they given already, or are they generated?
In the program synthesis benchmark 2, they already have test cases that include corner cases and a lot of just general cases, and they are taken from competitive programming tasks. That would be, and we also mimic the same competitive programming where we would make some of the tests visible, not only those that we give in the very beginning, but in those on which we also test each program. And then once we test on all of those validation tests, we also test on the hidden tests, which would.
Okay, but this is just an artifact of the benchmark. So in real life, you never have test cases written. So in real life, if you want to do fully autonomous programming, you don't have test cases. So can you elaborate on how you would realize its vision in real life, outside any given benchmark or any given artificial setup?
Yeah, so if we have only a natural language description of what needs to be done, then we would have first program, and then it should be cider T or something like that. One more block here that would generate tests for the program, and I would maybe even start with the test-driven software development. So I would probably generate a little bit of tests for the natural language description first, and would generate program from this so that we have the same, a little bit of tests and the natural language description. Then we would have program, some maybe failing tests, but then we would expand the test cases and and update the program in parallel. So I would think that would work, but also check that the test cases are not too similar to the previous ones. I don't know if fuzzy approaches would be there, so it doesn't have to be a language model generating all the tests. There can be other test automation, automated generation of tests tools applied there, but they should be in the loop if we don't have tests, because we relied in our correctness evaluation of the programs, we relied mainly on tests, but we have 200 tests for validation and 2,000 for final identification whether the program is correct or not. And that is what also, by the creators of the benchmark, it was also advised to use that number and that exact number of tests.
Okay, so since my job is to be opponent, I want to push you here a bit. So you say fully autonomous programming. I would say that what you do is a fully autonomous solution to those particular benchmarks. So the scope is much smaller than what you claim. Would you argue against for that?
Yes, I would actually agree that it's exactly for this setup when we have tests and when we have natural language description and we know that our test has good enough coverage, but also because it's competitive programming, so a little bit to maybe argue, but I would mainly agree that this is not fully autonomous for any programming problem in the world. And we also don't say that it's fully autonomous for any programming problem, we just say fully autonomous with language models. That's what, for example, we can do. But we also mentioned in our paper that it's for competitive programming, and those competitive programming, they are more complicated than just entry-level programs in Human Eval or in MBPP and other benchmarks. So they do test some coding abilities that are more advanced than entry-level programming. So I would say, good performance on those benchmarks says about models and cider tackling the higher complexity than entry-level programming. But of course, not any programming task out there in the world without any tests. Well, I cannot say that it can generate something without tests, because it does have tests so strictly coupled in the architecture. So that I agree with, yeah.
Thank you. In your presentation and also in your answer right now, you emphasized a lot on this Git commit step.
Yeah.
My understanding is that it's a pure implementation detail, but
It is.
perhaps I'm wrong. So can you elaborate on why
Yes,
you
I
emphasize
can.
that much on this?
Yeah. In program synthesis benchmarks, they are used in genetic programming. And we also presented it in Gecko conference. So in genetic programming algorithms, they would store. It's just like one way to store our generations of programs, and then we can track generation by the commit number, for example. And that was something that, so my co-author was more from that field, and that was something that was more innovative for the field of genetic programming, how to represent each generation of new programs. It's indeed just an implementation, but somehow not too many papers that we have reviewed in that area, like from my co-author also feedback, that not so many papers do use these Git commits for tracking the progress. So that was something that we wanted to also introduce to that area. So yeah, as a good way, in our opinion, to track program updates.
Okay, so now let's move back to the core concepts here. So in Program Paper, one of the very first paper was GenProg, generative programming, and it meant generative programming. And for some months, the authors and the community believed that there were actually some generative programming happening with refinement over the previous solution. And then later on, the community discovered that actually it's always, so when there is a patch, it's a one-shot patch with just one single change of the solution. So today in this literature on iterative prompting, so I am convinced that we have very often two or three steps, like the first one is incorrect and maybe the second one is correct or the third one is correct. But I'd like to have your opinion, and if not quantitative evidence of the depth of the evolution in your experiments, in the literature, of what we see.
Yeah. For the depths of evolution, I'll jump to additional slides where we measured how many programs were created before the correct one. Yeah, here for this with codecs. So we measure EPG is access programs generated before we solved the problem, and Python and Blue and C++ and Pink. So we were wondering, like, how far would we arrive? How far in the tree would we arrive to the solution? So how many new programs we need, or how many steps do we need? And with codecs, it was like mainly. It's a little bit shown here. So mainly 10 steps, but then within 100 first steps, we would really have more programs solved, and it's just a coincidence it's 47 in both. And 47 is like, here it's like about 30, so we would need additional steps, more than 10. However, with newer language models, such as GPT, it's like 3.5, and then Llama that we tested even later, we could see that first steps, like within the first 10 steps, it is important. So we don't need to go further to 1,000. However, we also checked that, so one outcome is that we do need more than 1, 2, 3, 5 steps, like 10 or maybe 100 in terms of codecs version 2022, not version 2024, because we haven't tested 2024, maybe it's different. So version 2022 was, we needed about 100 tests, but then what helped us outperform this push GP was that we actually progressed further to 1,000. Because then when we cut off for our generalizability experiments, when we cut off at 100, even with codecs, and when we outperformed this push GP with 100, we could not outperform. So it was on par with push GP. So it really helps to go further in the tree, or like to push the language model to its sort of limit, so to keep iterating. We don't push the language model to it, we keep iterating. And we keep prompting it from different angles. And that helps than prompting just a couple of times. But with the later models, the second outcome is that with later models, with those that maybe also have seen, so with data contamination of PSP2, it's also the benchmark that is also available there on GitHub. We could see that more problems were solved within the first 10 steps. But still, with only 100, because we reran those experiments like 6 times with larger models, we could not outperform with 100 steps. So there's still potential with iterating more and more. So I would say, yeah, iterating just 5 times maybe is not the best, but then it's also a question of, okay, how much resources do we want to, allocate? And what is the gain? 1 or 2 improvements, one or two like competitive programming examples solved, and maybe we can already, as software developers who like look at the code, we can already get enough ideas from the first 3 generations. So I think this few prompts, so like few steps in prompting, they originate from the idea that we as software developers looking at code and looking at the generations that the language model suggests us, because yeah, we still need to revise it. We do not have infinite time to revise 1,000 programs. So that's also one motivation to have a look at only first 5. But with this fully autonomous sort of setup that we call fully autonomous, not for every problem at hand, but here we could see what it would mean to have 1,000 programs generated.
Okay, just to make sure I understand these figures here.
Yeah.
So the top is a zoom
Is a zoom into
of the second one, right? Of
into
the bottom
first
one.
10 out of the first 100, yes, it's a zoom in.
Okay, so and if I read, so the top figures really mean that most of the solutions are found directly with the first. So
Directly in the first
here.
10 steps.
But even the 0, like the 21,
In the 0,
highest
the
bar.
first generations of the programs, yes, and it can be data contamination for those exact, but it still does not amount to. So this is 21, 24 out of our all experiments with all 3 arities. So they can be, it's not unique, it's just solved.
Okay.
So maybe one next step we could do further is just to see how many unique ones are there, but I don't have numbers for it.
Okay. Thanks. So, still here on CIDR, because we are there for now. So, there is a description part when you describe the bug, or you use another model.
Yes.
So, what the prompt here is?
Yes.
It?
Yeah, we tried 4 prompts, and we tried a little bit of different, like modal verbs, should or must the code, like there is clearly a bug in code, or obviously the error is in this prompt. So what we have input-output pairs, right? We have tests. So, and we also have output of our program. And if it does not match, then it means this input-output pair does not match the output that is expected. So we provide the task, so the specification, and we provide what output we expected for what input, but it returns a different output. And then obviously there is that, and when we have a completion model, text completion model, that also understands a little bit of code. So we had here like GPT-3 that would generate what is the bug. So, and then whatever comes after these 3 dots would be placed here instead of the bug. So fix, and then fix this error.
Then I'm a bit confused. I don't see where is the summarization here happening by another LLM.
Yes, so while it auto-completes what the error is, it summarizes not what exactly the code does, because what code does is specified by this task description, but it summarizes what it thinks the error is because of an unexpected output of OP for the output, while the output O was expected for this specification. So by auto-completing what the bug should be, it should describe what does not work. And
so are you saying here that the ellipsis is the end of the prompt?
Sorry,
the ellipsis here is the end of the prompt. The error is that?
The end of the prompt is here before the arrow.
I see, okay. No, but so before the ellipsis, before the 3 dots.
The end of the prompt is, obviously the error is that, end of prompt.
End of prompt, I see, okay. Okay, so okay, I see.
We have looked at what model generated, if that was the question. Or
So here the prompt contains some execution data with the must return O for input I. And then you want to, okay, does the prompt contain the buggy code or the impartial, the incorrect patch?
No, here it doesn't. We were taking care of the input token length so that we do not outgo it. We decided not to include the buggy code here. So we prompted the model indeed to only, based on execution, based on the output of the program, just say what is wrong. But in this experiment, in later experiments, we also it was like Code Llama, and there we also provided a program, the full program. So, but I'm now sharing all the results for this very experiment, not the generalizability.
Okay, because here, if the model is not given the code itself, the model is expected to reason about the bug just with the incorrect input-output pair which is given, right?
Yes, it is a more challenging task than when maybe we should have one prompt that has task and another prompt that has a program there, instead of describing the task and saying what is the not matching input-output pair. However, it was already able to solve bugs in this point. So sometimes, yes, the model would generate. It just does not output the correct input the correct output for your input, and that's it. So that was not helpful. But what was helpful is that it did not. It does not generate something for us. Yeah, we have this example here where we have do something with every second digit, and it starts with the second digit, but it just started with a different one. And every other digit starting with the second digit. So yeah, it would be still a little bit repetitive, but it would show it would give a good, debugging. It would get a good debugging signal, so that the second digit would be the first one to start with, propagating something that is done in this Loon problem.
Okay, that's clear. I have a very technical question. You rank, so I'm still insider.
Yep.
You rank the 3 generated programs through tournament/lexicase.
Yeah, these are two selection types. I think I will not show slides on it. I'll just maybe explain. Yeah, tournament selection is when we, on average, how many tests pass, what is the test pass rate on average? But test pass rate for each test is the proportion of the sequence that it generates that matches the expected sequence. So we can have 80% test pass rate for one test, because the output would be, let's say, 1, 2, 3, 4, and if it generates 1, 2, 3, 5, then we would still have some string match here. And this test would not be completely 0. It would be still 80%. We have this score that we compute. Now, that's the tournament selection. So overall tests, what's the percentage of matching the outputs between our program and the expected output? In lexicase selection, in tournament selection, we keep those that have the highest average score based on this string matching. In lexicase selection, we re-rank in the sense that we keep the programs that pass one test fully, 100%. We re-rank them to be first because they probably those programs, they pass some corner cases, and we want to keep this passing corner cases versus passing everything, but on 80%. So passing one test fully in this lexicase selection would be weighted higher than passing many things, but on average. not better, like better on average versus better on specific cases. Yes, so that's lexicase versus tournament selection. But unfortunately, we couldn't see that. Well, one thing is that we could not see better performance with lexicase selection. So tournament selection, the default one that is like, okay, better on average, maybe that works. All right, yeah, it still worked well. We could see like on par, basically nothing really changed when lexicase selection was turned on for us. That's one thing. And the second thing is that this re-ranking, but also what you spotted on this like zero, like at the first attempt, many programs are already solved. So many programs were solved, and then the test pass rate would be from 0 to 1 on all the tests, much more frequently than it would be gradually increasing, and then we would actually use this lexicase. So it was more important for CIDR to achieve at the prompt, the debugging prompt, that would work better for the next LLM to generate the debugging, like patch, versus re-ranking. So re-ranking didn't mean that much. It was like we were searching more for a better working prompt, as we understood later, rather than searching for what the program is better in the intermediate step.
Okay, thanks. That's very clear. I understand. And now it comes back to this question we are discussing about the actual evolution happening.
Yeah.
So again, going back to GenProg, looking at your results, referring to the related literature, it seems that there is very little evolution happening for real programs in that context. So, and it's actually very hard to drive evolution with a numerical fitness function as the one you're describing right now. So this is a claim I'm making. There is very little evolution happening. Do you agree, disagree?
I agree in terms of evolution happening as like generating the full program from scratch. What I would see space for evolution right now, and based on the experiments that we have done, is that like generating program, not a full program at once, because we either like guess it or not guess it with the language model, and with a better prompt we guess it better, but that's not where like we should not guess the full program better. We should maybe guess the next line or next set of lines better, and then that's what would help, maybe in my opinion, software engineers more, where we are stuck now, we need the next best step. Let's use the language model to help us with this next best step, and this next best step should be like really clean and clear, and we just shouldn't need to debug it. Then that's where the evolution should be. So we shouldn't like create the whole full program from scratch maybe at once, like incrementally create a program and then revise it, incrementally revise it. That's where evolution maybe should go, but not like creating one program at a time, a full program. Although I have tested many of those that create like full program, function level programming, program generation, yeah.
Yeah, I follow you, and what you're describing is not, so the evolution is not driven by the fitness function. Again, here the test cases, this one is a bit binary, more about the
added functionality. Yeah, one added functionality after another added functionality. So quality of code increasing with every next like step that is used, let's say, from a language model. But we don't have those benchmarks as far as I know, that would like incrementally evaluate whether the model suggests the next best step or not, and how well it does it. But that would be helpful.
Yeah. Agree. So my last question about CIDR, and then I will give you the mic. It's really about this big picture of iterative prompting versus agentic. What's your take on that? So what's the definition of iterative prompting? What's the definition of an adjuncted system? Where is the state of the art? So what's the best system today on that line?
Yes, for iterative prompting, we still solve one and the same problem, and we just we prompt it once, we don't get the full solution, we iterate further, maybe with another approach, few shot, chain of thought, etc. Different other prompting, but we work with one and the same problem in program synthesis, for example. Then when we have agentic frameworks, to my understanding, that is when we have several agents working in parallel on the same goal, for example, code generation. And there could be one agent RTT, one agent CIDR, one agent just GPT-4, just as it is, regenerating all the time. So different approaches. So one agent is one approach to the same problem, and then those approaches can compete. And that's more resource, requiring more resources. But then it's a little bit like machine learning with one method versus ensemble machine learning. When we go from just iterative prompting to iterative prompting in agentic frameworks. But agents, they usually also work iteratively or repeatedly. Iteratively. So they try the same task several times, and they just collect information from all the agents now, and then they would perform the next task based on the understanding of all the agents. And then there could be useful information from another agent, but that this other agent, like GPT on its own, could not maybe solve this problem, but it got some solutions from CIDR or from some other language programming framework that it can use in its prompt to iterate further and arrive at the problem solution better. So those are agentic versus iterative. And you also asked about state of the art. I have seen papers on self-debug, iterative, iterative programming with debugging attempts and etc. I would not say that there is one copy. It all depends on the benchmarks. There are SWE agents that work well on fixing GitHub issues and SWE benchmark. It again really depends on what your task is and what would be the state of the art. But I would say agents with language models now are developed more than agents that are rule-based, because there were agents before, like agent-based programming before, and they would be more rule-based. So one agent would not use an LLM; it would just use some very fixed program that would have very predictable outputs, and they would just communicate to each other as just maybe different modules of a program. But now, it is improved by maybe a little bit of this creative language modeling outputs. Yeah.
So do you like this line of research on LLM agents, or what's your opinion on this, informed opinion?
How to say, I think it's promising in the sense that we can learn from different approaches at once, collect this information in one source, in one agent that will be a router agent, and propagate further to the same on different other agents. So it's very curious to try. I would be very curious to try, yes. So in terms of liking or not liking, that would be the next step after LLMs and after iterations with LLMs, after iterative prompting. But then, in my personal preferences, that would be okay, how can we make smaller models more effective? That's maybe not what agents would help with, but it's more on architecture side. It's not something that I explored much beyond the early bird here, but that is something that probably will be, because we will need language models, maybe agents, maybe just language models that would run on our phones and would not require that much energy or would not draw on our battery that much. But still help us in everyday tasks, so in some simple learning of programming. So it's there is potential in agents, but it's also nice to create models that are not that huge.
Okay, thanks. I take a break right now. I have many other questions.
Great, thank you for your questions.
After when he has not taken them.
I'll just take a sip of water. It's behind me, so I'm here with you.
Okay, so Mr. Chairman tells me that I continue. So
No, I'm fine. I just got my water. It's fine, and thank you. Maybe we should also ask the audience if someone needs to leave early or something, then maybe we can have a break. No? Okay,
Good.
we continue.
So let's take a break from technical question and go back to a high-level question. Paper 4
Yes.
is very different in nature from the 3 other papers.
Yep.
And so I'd like to have the full story here. So
Yes.
either you started by paper 4 and realized it was a dead end and moved to something else, or you started with the rest, but you really wanted to do paper 4 and then you did paper 4, or paper 4, you know, maybe your supervisor or somebody came and say, we need to write this paper.
Yeah, don't worry.
What the full story about paper 4?
I can share the story. Yeah. It maybe will start a little bit before even my PhD, because I did the master's in computer science for sustainability, so sustainable software engineering and software engineering for sustainability. So this question of how much energy we spend versus gain of like research results that we have in language models, for example, it's always like relevant or somewhere in the back of the head. So that's from my master's. Now, how was the story? So I started with early bird paper, and I had to fine-tune a lot of small models, and also 10 times. It also was, a lot of, I understood that, okay, my research now is like, yes, I do get plus 2% accuracy, yes, with smaller models, so I can show and I can really tell people that, yes, I have tested it several times and I have found statistical significance of these smaller models. Okay, nice, but at what expense? And then we ran like a lot of models and we fine-tuned a lot of models. In parallel, so in parallel and also closer to the end of working on this early bird paper, so Max also joined us, and it's my co-author, and like with Leon and etc. So we, as a group, were all like interested in these sustainability aspects. And I already started with some literature review, but I also helped with this some literature review that was not energy efficiency oriented. But we also wanted to see what are the common interests, and so we created this paper a little bit in parallel to early bird paper, but then soon after it we created this study on how open the models are and how much energy they use, and also there was Bloom model that showed this like 5 times more carbon emissions for language model training versus average car usage. And that's a lot, so we decided to see, okay, in language models for software engineering, where are we? Does that answer your question?
So my understanding of your answer is that, 1, you did your master's degree in a related field, and 2, you had the collaborators in the group who were
also in the same
interests.
Yeah.
Okay, good. So for paper 4, in my group, we do share everything, but we really don't know about what to share for measuring energy footprint.
Yes.
So here, what are your actionable guidelines? What should I tell to my PhD students when I go back to Stockholm in terms of what information should we give?
Yeah, that's great. I don't know if I have it on the slides, but in any case, okay. So in language modeling, we have GPU usage and CPU usage. So sometimes we evaluate, and then we may only need CPUs, right, for testing or something. But when we train, we use GPUs. So what type of GPUs, what amount of RAM is needed, so that was missing in so many papers, for how many hours those GPUs were used. And if it's 2 GPUs in parallel, were they always on or not? And it's nice to use maybe, I don't know if there are profiling tools for GPUs. Yeah, sure they are. Seeing for how long the GPUs were used out of the whole experiment, because the experiment may last like 10 days, but of those 10 days you would evaluate as well. And then our estimation on how much energy usage was happening is not, if we use like several GPUs, but those GPUs were not used all the time, then that would be a larger number than that actually was, for example. So yeah, RAM, type of GPUs, maybe number of hours, and CPUs, number of cores.
Okay, I guess, so we use clusters for our experiments, but my understanding of the stack, and maybe this is my ignorance here, is that So probably for GPUs, when we allocate, when we book nodes with GPUs, I think we have 100% of the GPUs. So in that case, we might be able to report on those two factors, so type and number of hours. Is that possible to time share a GPU on a big machine? Or so if we book a GPU for 10 hours, does it mean that the job is running for 10 hours 100% on the GPU?
No, there should be profilers that say for, yeah, I think we have this one, it's similar, where they show like, okay, now GPU is booked, but at the highest usage, or now it's booked, but it's not used.
Okay. Okay, and so here my gut feeling here is that the problem is much harder than the basic information that as the ones we are discussing right now. So do you think we would need better, or we would need better support, or we need to activate advanced features in the machine learning framework we use to report the information you need? Or?
Sorry, I didn't get your question.
Do we need to have more sophistication than just reporting, number of hours and type of GPUs? So do we need something more advanced for measuring what we want to measure?
Okay, so in this study, we used an online carbon emissions calculator from the GPUs and from the energy. So there are studies in that also like say, okay, what details are needed, and yeah, for each experiment. And some of, like, it depends also on cloud provider or an actual GPU that you're using, and like in-house. They share that more details are needed, but that if not more, but at least having GPUs a number of hours will allow to approximate all the other, like estimate with some assumptions. And those assumptions would be generic assumptions that this was a GPU that would require this much, but okay, maybe GPU of this year, of that year, that would be more fine-grained, but at least having this assumption would already be enough. I can maybe scroll to this, like what the calculator actually used. Yeah, I think we have it. Because there was more information and we did make assumptions. It's also in the paper. Yeah, we are arriving there. Yes. Yeah, so RAM, runtime, type of course, like CPUs or GPUs, and the number of cores. And this is the green algorithms calculator online that we used. Also, like where, if it is a local or a cloud service. So for cloud service, it's important more because they like I don't know, Google cloud providers and other cloud providers, they report different, there is a metric on efficiency of the data center, like how green the energy is that it uses. For example, some data centers use waterborne energy, and some of them use like other types of energy. So that would also influence.
Okay, so that's a perfect slide for substantiating this conversation here. No, here is my biggest problem with that. Here is that I believe that carbon footprint is irrelevant in this case because what we're talking about is energy, and we don't know what the source of energy which is used. So I claim, and you can argue, that the right metric is not carbon footprint, is really energy.
Energy and source for energy, yes, and that's why location for the, But then because we wanted to still estimate, well, at least energy usage, but then we found more carbon emissions calculators than energy estimators, because energy estimators would be profilers, and then we would need to rerun all those models, so like retrain them again. And so we did not find tools for that. We found tools for carbon emissions, so that was something that was doable, but still we could see the impact of, okay, what's the carbon emissions or energy usage.
Okay, so here your answer is yes, but we had tools for computing carbon footprint, so we did that. Is that what you're answering?
Yes.
So what is the quality of this model here, this paper and this model? How valid is it?
How we would evaluate validity of a tool. Yeah, it has a publication behind it. It has
sure.
Yes, has usage. Maybe it was widely used in other In other publications, we had a look at a couple of tools. We have found out the one that is detailed enough, and we trusted that because also it had like scientific basis underneath. But we didn't go into like comparing all of the tools and then, okay, with this tool you can estimate this much carbon emissions, and this tool this much carbon emissions. And I would agree if they were estimating energy, I would maybe prefer also energy, because if it was like, okay, in Norway it would be high, like waterborne energy, and in France maybe a little bit different types of energy, and like, yeah, Sweden also maybe waterborne, yeah, so either. That would depend, yeah. I mean, if you're asking now, okay, why didn't we do more or differently? Yeah, we would prefer to do differently, but we also did what was in the time constraints. And,
okay. No, I think I'm hearing that you kind of agree with me, genuinely. So that's and if I have one tip here is that it's not because there is a paper that this is valid results and valid research. I'm sure you already know that, but the presence of a paper doesn't mean anything about the validity of the conclusion.
No, we need to like look into the paper and see what their threats were and how they evaluated their validity of their tool. Yeah.
Okay, so that's for paper 4. Now going back to paper 1. So we already discussed about the key aspect, which is whether we do anomaly detection or reasoning with the expected behavior, and we do anomaly detection. Now, the thing which I'm missing a bit here in paper 1 is the intuition of the research. So is there some previous work showing that going to early layers is valuable, or is that like your own intuition, or what's the intuition here?
Two pieces here. One is there is already work on like which layer would work better for which task without reducing the number of layers. So they would sort of do profiling of the transformer, but like not profiling, okay. So they would choose one layer out of the full model, intermediate or later ones, and predict and use it for some classification tasks. So that's literature, and they also use CodeBERT and graph CodeBERT and other BERT-based models for code, where they were trying to see, okay, maybe we don't need to use the last layer all the time, but some intermediate layer does work better as a whole layer. But my intuition here was that, okay, but we don't need to use only one layer. We have all of them. Why don't we like combine all the layers? So that was my own curiosity. The second piece of curiosity was maybe also historical. Okay, I was reading the BERT paper. I was like learning about transformers, reading about BERT paper. And then there was there was a statement, okay, we use CLS token when we then first token from the last layer, and then we fine-tune the models so that we use just this token and nothing else, and on classification task. And there was no indication, to the best of my findings of research, that they tried something else. It was just an architecture choice that was not maybe based on more experiments, or at least they were not listed there. So, and it was my curiosity again, what will happen if it is another token? What if it is more like CLS token, but from an early layer, or full early layer, or all of the like combination of early layers? Because we already have information there, and it can be useful as shown in another work for different various tasks. But then we can combine them all. What we saw in the end, that combining all of them with maximum pooling, especially with weighted sum of layers, it sort of it didn't perform better because, for one, models are indeed like they're pre-trained on so much data already with CodeBERT, for example, that CLS token is already optimized. So if we initialize from pre-trained weights, then it's beneficial to work with the CLS token. And that's also why in pruned models, we still use the CLS token. So this was the one that would gain information of the whole sequence. Now, so weighted sum of all of the layers did not help, but then removing information that would be maybe a bit of noisy, or like CodeBERT is a generic model still. But if we want to use it for classification, we can fine-tune it, but we can also use only the layers that are useful. Here, as we saw, only some of them, not all of them, and further fine-tune on our task.
Okay, so what I miss a bit in paper 1 here, as opposed to the others, is to get the actionable bit of knowledge that you contribute to science. So can you again rephrase what the new thing we learned that we can use for further experiments or further systems in paper 1?
Based on our empirical evaluation, we have learned that on binary classification tasks, such as classifying into buggy code and clean code in anomaly detection manner, we can achieve better performance fine-tuning smaller models. Whereas for classification tasks into multi-class classification, so into 3 or more classes, we can observe the trade-off between smaller models, so less resources used, and accuracy or whatever our target metric is. Because with smaller models, we actually lose, like in more complicated tasks, we lose information that by cutting off layers. But when the task is small and simple, and this binary classification, this information that is otherwise needed for more complicated tasks is actually maybe diverting the model away from this very small task for which we don't need that much complexity in the model.
Okay, so if I rephrase a bit, what you're saying is that for some tasks, the early layers are enough, and you don't need the other ones.
Yeah, I like the laconic rephrasing. Yeah.
Okay.
I'm maybe not that laconic.
Okay, interesting. And then, so this morning you had this slide on encoder only, decoder only, encoder, decoder.
Yes.
And so today, basically...
Most of them are decoders, yeah.
Yeah, even for binary classification. So...
Yes.
What's your opinion or your vision on where is there still a future for encoder-only models? Are they still performing on some tasks compared to decoder-only? What's your vision?
Yeah, we could see that on defect detection on multi-class, like syntax type defect classification. The performance was like 90 plus accuracy, so they do perform like encoder models. And this is CodeVert, like it's not the very recent model. What decoders do, they still implicitly have representation of sequence, but historically encoder plus decoder, encoder would encode the sequence, decoder would decode the sequence. Decoders, when they are used just as they are, they still have representation of the sequence, and then there would be, if it's a classification task into like binary classification, I would assume they have a classification head on top of the decoder that they would fine-tune. So that's still a transformer, that's still a attention mechanism. The architecture of encoder and decoder, they still use attention layers and feed-forward layers. So it would be interesting to see how the results transfer from these encoder results to decoder results, but encoders are more like historically used for representing sequences. So if I were to represent a sequence and then classify it, I would still use an encoder. Maybe I'm just biased because I know about this historical development. However, I would assume that honestly, I would have to really look at where the representation of the full sequence lies in the decoder, because decoders are optimized to predict the next token from the context, from the whole sequence. So they should have representation of the whole sequence. But where it is, last layer, first token, last layer, weighted sum of all the tokens, or like all the parameters, that I would have to have a look at. Like right now, I cannot answer this, but I would need to have a look and then see if the same very experiment would apply. You were asking about the big vision, and do we still need encoders for anything? Well, this paper shows that we still have good performance on like 3-class classification task with an encoder model. However, because generation is now so widespread, so popular, then it's for predicting next token based on the context, decoders perform well, they scale well, and we like the layers that we had in encoder, we can now just omit them and have very similar decoder layers, because there was this mechanism that would fuse encoder output to the decoder, and that would be additional complexity, but we dropped it and we increased just the decoder, maybe with the same or more of the encoder, of the layers that would otherwise go to the encoder, but we used them all in the decoder. So we could expand the network. So I understand the gains, but it's mainly because generation is so impressive to have that we have development for encode in the decoder part and the generation models. And we could also see that those generation models, they can output a class number even if we ask it in a prompt, like what would be the class. But they learn the distributed representation based on the context versus having a special like layer that actually classifies. But having a layer that classifies our sequence is simpler. We don't need that much pre-training. So if two models, one encoder and one decoder, would have the same amount of data they are exposed to, decoders would, in my opinion, if they need to like generate not without the classification layer on top, it would just need to generate the output as a textual output to our classification task. They would need more data because they need to learn more about the representation. While in encoder, we just learn the representation and we train the classification head, that's it. But decoder needs to somehow understand our classification task and then generate the correct answer. So yeah, I would see different use cases. Just that's my answer, maybe.
Okay, thanks. So I think I'm done with all my questions. To summarize, so Cider is really cool that you did it early, and so many others have been exploring this idea of having like some feedback loop, and so that's I'm 100% convinced that this is the way to go, and so commercial products will do and are already doing this kind of technique. So that's very valid. Round-trip translation, there is something neat here with respect to reasoning with the specification and coming back to the implementation. I'm not sure the core use case is repair, but I like, again, I like the elegance of the idea. At least as a intellectual curiosity, it's very interesting. The paper one, there is this question of what's an anomaly in code, and is that really an anomaly? So what kind of problems we actually catch, and that's the whole related work, not only your work here, suffers a bit from this question here. So what is the kind of bugs we actually detect? And it's really an important question for software engineering. And you answered well to, we discussed paper 4. So, your work is very relevant. Your questions, your answers to my questions today were grounded, given with assurance. So thanks a lot.
Thank you.
I thank Professor Martin Mockers for his contribution.
I'm okay. I'm still ready for more questions. Yeah. I'm in the flow.
And I call upon the assistant professor, Johans, to close the
Yeah, first of all, I guess it's also an overview and assessment of the contribution of the thesis. I agree with Martin. I think the contribution to the software engineering community is significant, and it's a cross-domain research topic, and it covers different communities, and it's really, really crowded. Lots of people are working on this, and more people are working on this. But I think you did a fantastic job. I especially like the novelty of especially the first 3 papers. I think the angle is very unique, and I like them all. For example, for the first paper, you check the contribution of early layers, and we know that ignoring early layers was why like the old NLP models didn't work well, right? And I think the work of checking the combination of different layers is really, really interesting. And the second one, you didn't just directly try the multi-agent framework, but instead you combine the framework with the traditional genetic improvement. So I think that angle is also very interesting. And third one, I think I listened to the keynote of ICSI this year, and I think it's by Martin from MIT. And he introduced a work that, which is similar, but he used it to repair the software vulnerability. And when I listened to that talk, I was thinking, whether we could use that for program repair, and you already did it. And so, yeah, a really interesting work. And last one, I think it's really important, the sustainability aspect. So overall, I like all your papers, and I think the contribution is significant. So I have some questions, and some of them have been covered by Martin. Let me think about which one to go first. Maybe I can start from the last one. So there are different categories, different colors. So my question is, what about your own papers? Which category do your own papers fall into?
Oh, okay, that's a good question. So thank you for this. So CIDR and RTT, we don't fine-tune any model. In Earlybird, we do share. I just rechecked yesterday just to be able to answer this actually. So we do share the hours that were trained were required for one epoch, and the GPU that we use one GPU. The RAM. So I would say that we share, like we are here. We hope to say that we're here. But then again, it's for this carbon emissions estimator that we used. Maybe for energy efficiency and more fine-grained analysis, but we kept track of our details. So I think we can also provide more if needed, more details if needed. Yeah.
Thanks. So I think you discussed how they measure the sustainability, right, in the papers. But I think nowadays for LLMs, more and more researchers are just using the API of LLMs, for example, and they don't really train or fine-tune their own models. And so did you see any papers releasing their token overhead, for example? Is that a popular way to measuring the sustainability? The token overhead.
Token overhead,
yeah.
Overhead or just usage, token usage?
It's just overhead.
Yeah, okay. So in this paper, we did not have a look at this or indication for how much of the language model they used in terms of tokens in, tokens out. Otherwise, but I agree, it's an indicative measure in the case when we do not have access to the actual model and we don't have our GPUs on which it runs. It runs on the proprietary cloud resources, etc. So the answer, yes, we did not have a look at it. It's a nice indication now, but back then, I think it was when we were collecting information. It was until 2022. We did not have this information to collect. Yeah, but it's a good suggestion. Yeah.
Thanks. So I'll go. I think I have some general questions regardless of a specific paper. I realized that when I was reading your thesis, I realized that you use PSB2 and human eval a lot.
Yes.
So what's your principle of selecting those benchmarks, and how do you avoid the data leakage problem or data contamination?
We include data leakage problem in our threats indeed, okay. So why those two benchmarks? Especially in CIDR, we were sort of in between this genetic programming where PSB2 was used very frequently, and in language models, human eval was used frequently. So we just used those that are leading benchmarks in those two fields. So that was, and we have a lot of models to compare to. Also to compare how LLMs with CIDR compare, how CIDR with LLMs is compared to just LLMs without CIDR. So that was why we used human eval. We needed tests. And we, so tests, maybe a test pass rate was the primary metric in CIDR and also in round-trip translation. So we really We did check Code Blue and we did check our other metrics as well, but test pass rate was the one in which we grounded, so we needed tests. And also this human eval Java was created like by introducing bugs into human eval Java benchmark. It's not, because here we repair bugs, right? And human eval is just a data set for instructions and program solutions for those instructions. But human eval Java was a curated data set where they created bugs, they injected bugs themselves in, and this probably was not seen by the models, but then maybe by later models, yes, already they are exposed to this benchmark because it's on GitHub. Yes, so those two benchmarks, in CIDR, they were most popular in the field, and in RTT, we used the one that is, probably not seen by the data. So for data leakage, yes, human eval might be seen by like GPT 3.5 and Code Llama. So now, as I mentioned, this CIDR extension is under revision, and now we have run tests. We have run more generations than just one. So in our initial exploration, we ran just once. Now we try to repeat experiments and see how whether they perform more or but that's for repeatability. No, that's for a different thing. Now we cannot measure whether, for example, for GPT 3.5, we don't have a data set on which it was trained. So we cannot overcome the possible effect of data leakage. However, we saw in this EPG graphs that I was showing, 10 first and 1000, that not all of them are solved from the first try. If they were all solved from the first try, it would mean that the language model just memorized this benchmark so well that there is no meaning in like iterating over or actually testing on this benchmark. So the fact that we had solutions further in our iterations means that this benchmark was still challenging for this setup or indicative.
That's the same answer. I actually asked this question to the leading developer of Code Llama, and then he gave the same answer. It's like, even with the data leakage concern, I think it's still challenging for lots of LLMs. Right, thanks. So for the PSV2, how realistic do you think it is? I mean, the code, how realistic it is? For example, Sweetbench, lots of people like Sweetbench because they think it's realistic. It's from GitHub. It's from real scenarios. And what about PSV2?
PSV2, they are realistic as realistic as, for example, Code Contests benchmark that was used in AlphaCode. So it's just two different. So in SV Bench, we have GitHub issues and we have real repositories and production level code. And PSV2, we have competition level coding tasks. So they are not like real life tasks, but they are those that check maybe programming abilities of a more complicated level than entry level.
Right. Okay, thanks. So I'll ask, I think I'll start from the first paper, but I don't have many questions for each paper, so hopefully I'll finish quickly. And the first one, so you check the combination of different layers.
Yes.
The problem is how do you know which layers to select before your trial? Like, can you predict? Can you have?
So one, we do not just select several layers. We do the full grid search over the layers. So we do it really thoroughly from 1 to 2, 3, 4. So we just check all of them. That's why there were a lot of fine-tuning and a lot of concern about, how much energy it would use. Now, in pruning, there are different methods that would, based on like what weights are activated in what layers, they would maybe drop some layers. So there would be sensitivity analysis for pruning, and then some layers would be pruned. However, we don't do this. We just keep the first layers, and we do not keep like 2 random layers out of 12. We keep only the first ones, because that's how the model progressively learns a larger and more difficult task. So omitting last layers intuitively would omit a little bit of complexity that is learned further in the representation.
I guess my question is, sorry, I didn't make myself clear. So I think my question is more about, is there any pattern that you have observed? I understand you could select the layers based on like fine tuning and based on assessment metrics, but have you observed any pattern?
Yes, I will just go to this slide here. So that's, for example, CLS tokens from early layers. So we could see that middle layers with maximum pooling would give statistically significant improvement, but not that large. Middle layers and maximum pooling. So we were more thinking about not layers, but what operations would be giving more improvement, rather than what exact layer, but somewhere in the middle we could see a bit of the pattern. For the data sets that are binary classification, these are data sets with 3 classes, and we, as I said, without changing the amount of parameters, so these are combinations, these are not pruning, where we use like all of the layers. So still keeping the full size of the model would be the best.
I guess there can be more dimensions that you can analyze, right? There could be many dimensions that you could analyze, for example, depending on different tasks. Have you checked that?
More dimensions to models?
Maybe it would be interesting as a future work. For example, you check for different tasks whether some tasks they need a combination with specific layers or.
Yes, there could be some preliminary tasks like we have pre-training and fine-tuning. We can have a preliminary task to have an indication of which layers would perform best for what. But maybe it's indeed for future work, and then not only like combining all of the weighted sum of all of the tokens from all layers, but then splitting it even more in more fine-grained way. Would be. But then it would be even a larger grid search, and then we would see if we are expecting really large gains from such a huge grid search.
So, more general question: do you still believe in encoder-only models? Although I understand it suits more on classification tasks. I mean, if you check some introduction of different types of models, you'd say some people believe that encoder-only models do better on classification tasks, but what's your opinion? Do you still believe it? Or
they do better than other? I tend to check, not to believe. How should I answer this? Yeah, so I would not discard it completely, but I would still, if it's a classification task, I would first go with an encoder. If it's a different task, I would first go with the decoder, and then out of curiosity, maybe check encoder. But yes, I would tend to go with what is seen in the benchmarks. If the decoder performs well, then empirically, I would rely on empirical evaluation. Yeah, it's my answer. Yeah.
Thanks. So for the second work, so you have a ranking algorithm, right?
Yes.
You rank different solutions, but the LLMs they have their own ranking too. Like they have top K candidates.
Yes, they have token by token ranking. Yeah.
Yeah. So how does your ranking result compare to their own ranking results?
Yes. Okay. So ranking within LLMs and the top K most probable tokens, they are about the next token, or about maybe the next sequence. Here we rank the full programs and also based on tests. So we have a completely different signal, not from the distribution, but from the test pass rate. So it's a coding signal more than the patterns in other code bases that we rely on here.
Yeah, but you can still use LLM, like use the information provided LLM.
Yeah, we could have introduced it in addition to tournament or like case selection, like an additional signal for ranking. Yeah, we just, it's maybe for future.
I think that would be interesting to have a look. Yeah. So for this work, I think one big problem for multi-agent framework is their cost. So have you checked your cost, and did you make any effort to reduce the cost of the framework?
Yes, we did check the costs with GPT-3, 3.5, and yeah, then we used Code Llama and Llama 3 in other experiments. So now in 6 restarts in like an extended generalizability experiments where we had 1 restart of coder with different realities and of codecs, and then 6 restarts with GPT 3.5. Then we had about, I think, $500, $600 for all of the experiments. That was the cost. What we tried to do to decrease the costs were we checked also GPT-4 and we checked other, like we ran small experiments, not with all triarities, not with all hyperparameters, and try to see what lengths of the tree should be and what would be the cost of each hyperparameter setup. By running just one check, and then we decided that GPT-4, for example, would be too expensive. We stayed at GPT 3.5, so we did this cost analysis in this way. We started with GPT-3, so it was less costly than 3.5. And also, yeah, as I said, evaluated small experiments to see how many programs in total we need to generate and we can generate at our budget.
I think for cost, as I said at the beginning, we think now more importantly, we check the token overhead because the cost of API changes quickly, actually. Yeah, like OpenAI, the GPT APIs, it becomes much cheaper than when it first came out, right?
Yeah. The costs
about
they evolve, and that was one. So the token overhead, and then that was one of the reasons why we did not include the programs that were buggy into this model-generated prompts, because it was either not fitting because programs were too long, or they would generate more costs. So we decided to still just have this execution-based signal.
Okay, thanks. So for the round-trip translation. I see that you explained your motivation, and I really like it that it came from your own experience. Yeah. It looks like, so when I read your thesis, I feel like you believe the power is in the translation. It's like you translate from the buggy code to something else, then you translate back. It just feels like you believe in the power of the translation. So you think it's because of the translation, the bug is vanishes in some sense.
No, we based ourselves on 2 main hypotheses. Maybe not the translation itself, but regression towards the mean and naturalness of code and naturalness of clean code specifically. So if we still stick to the word belief, so we more think that more clean code is visible in the training data, training corpora. And then because models tend to output tokens that are more probable and they're also more clean, so they regress toward the mean, and the mean is clean code. So that's but not the translation maybe. But
yeah, but if that's the case, then why, if you translate one code to another, then back performs worse than you translate it to natural language, then translate it back? If what you explained is true, I assume that the first scenario I said, means you translate one language to another programming language, not natural language, programming language, then translate back, it should perform well, right?
It was the case for translation between programming languages that the models were fine-tuned to the degree where they would reproduce bugs in the new language as they were in the previous language, and they were fine-tuned for more exact translation. But then the models that produce text from code, they sort of generalize to a higher, to a level that is further from code, to something that is just summarizes the code and does not follow line by line, but summarizes it. So we just needed to go a little bit more abstract and then further back. But this, because the models translated the code that well, they did not regress towards any mean, they just translated well That was why we think they did not lose the bugs on the way.
I agree with you. I think as probably the natural language thing is the key here, because large language models they also understand natural languages very well, and so you summarize the code, you get kind of a specification, and then large language models, I mean, they understand those specification better when generate code. So probably that's the...
Yeah, maybe also because the way they're trained, so there are more text-to-code tasks in the training corpus, so like visible. Yeah, maybe more than just the power of translation, translating mechanism. It's the power of this extra step rather than the step being a translation. That was helpful.
Yeah. So that's related to my another question. It's so the correctness of the specification you got from the translation. I think it depends on how buggy the code is. Because you could have a completely buggy code, like nothing makes sense, right? It's just or you could have one, or you could have one code with one token, that is buggy. So have you checked the difference between these two kind of scenarios?
No, we didn't, but we also had only one-line bugs that we would maybe tend to say that these were small bugs that would not change the logic that much, so that the logic was still deductible.
So you said that the buggy code is just one buggy line, right?
One-line bugs.
That may not affect the specification generation a lot.
Exactly, If it was completely buggy code, then the summarization would be of a completely different function. And it would help to have the golden or the source instruction instead of generating the instruction.
Yeah, so I think it would be interesting to explore the correlation between the degree of the incorrectness.
If there are multi-hunk, multi-line bugs, then maybe that would we would have different results in RTC.
It also depends on the ability of the LLMs in summarizing the code, right? So have you checked that? I believe that the more powerful the LLM is, the more...
we checked, we saw that the larger LLMs work, larger doesn't mean always more powerful, but here, so with LLMs that were larger, there would be, it doesn't say, it says how many bugs were solved, it doesn't say the quality of translation here, but still the performance increased as the language model size increased. But also here, Santa Coder is just better performing, although it's not that large, but better performing than, let's say, 6.7 billion encoder. Still, they have a good degree of understanding of code and summarizing code, So we just chose those models that would summarize rather well, except for maybe PL-BART and Code-T5, because they're much earlier and have worse performance on code summarization as well,
Thanks. I think code is answered well. I'm checking whether I have other questions. One, maybe not a question, maybe a comment on the introduction or related to work part of the thesis, is that I realized that we introduced the evaluation of language models and also evaluation of code language models. You focus more on the correctness of the but I don't know, just a comment, maybe you can also introduce lots of metrics and benchmarks on non-functional properties. Like fairness, efficiency, sustainability.
Also readability.
Readability, and privacy, things like that. Right. So one question about the multi-agent one, the second paper. Why do you think it's necessary to use multiple agents if you have a very powerful agent, like one single agent that is extremely powerful? Do you think it's still necessary for us to use different agents to collaborate with each other?
If we have one agent that is already powerful, should we have more agents or not? There can be cross-learning from different agents, but we would need to check if that is actually happening and if that benefits. So here we had several modules that would perform distinct functions, and that's why we called our framework multi-agent. So we needed an execute agent or execute module. We needed a rank module just so that we can progress with our algorithm, but it can be also called just multi-module network. In a more like general grand scheme of things, do we need more agents all the time? Yeah, I think in production environments, if we just have already reached the level that we need, and then we stop there because we don't want to use more resources. In research, it's always curiosity-driven. It's like, okay, maybe we can have better performance with multi-agent. So once there's enough research into multi-agent approaches, there would be maybe an answer, but I would be curious to see how cross-learning from multiple agents would work.
Thanks for answering my questions. I think that's all from my side.
I thank Assistant Professor Jejan for her assistance. Does anyone wish to speak ex auditorio? Doesn't seem to be the case. Then the committee will now withdraw to evaluate this.
Just wondering about my microphone. I'm muted or not? No. And now I'm probably muted. I just muted myself. I just muted myself? No? No. Okay, thanks.
Now I'll ask this question. Has the committee on dissertation satisfied?
So, Anastasia, the committee has read the dissertation, listened to your presentation today, listened to your answers to all your questions, and the committee unanimously approved your dissertation. Congratulations.
Thank you. Oh, wonderful. Oh, thank you.
Last but not least, every successful defending candidate from the department will get one special present from the department. I'm not sure whether you have looked at the walls of the department building. There are several big stainless sculptures. They are forms of different waves. And here's one small replicate of this. And you can read more information in the box.
Thank you. Thank you. Okay.
A report will be made to the Faculty of Mathematics and Natural Sciences. And I hereby declare that these proceedings are concluded.
Thank you. Maybe I can just have a word and I'll just put it. It's heavy. Part of the wall is heavy. Yeah, so I would like to thank you all for coming here. I would like to thank my opponents and reviewers for challenging questions, but also very nice scientific discussion that I will keep thinking about those questions and also comments, I guess, further. And also there's going to be discussion in the group, and I think I will learn a lot here. I would like to thank my supervisor, Leon Monen, for being such a great supervisor and great motivator for me to go on, continue even if some of the results were negative results at first, but we could then turn them to positive by more and more exploration. And I think the way that you believed in and have been believing in all of your students is what makes a group successful. Thank you for that. Thank you for my friends. Thank you for everyone if someone is watching online still. But yeah, I'm very happy, and yeah, thank you for being here. Thank you. Yeah. Thanks. Thank you. Thank you. Okay. I need to. Yes, maybe I should unplug.